So in this video, we will do the last proof of this course, the proof of a theorem about existence and uniqueness of solution of stochastic differential equations of the form 6.4. Now, this is in a sense what everything we've been doing up to this point has been designed to solve. So this is designed to show that we can construct processes implicitly using an equation of that form, as long as the function mu here, the drift term, and the function sigma here, the volatility term, satisfy reasonable regularity and size assumptions. So the assumption of the theorem, the appropriate regularity of the drift part and the volatility part to ensure existence and uniqueness of solutions such as D are the following. Now, this is very similar to what you see in ordinary differential equation or some nonlinear partial differential equation. So what we want for mu and sigma in terms of regularity, we want them to be Lipschitz continuous in the x variable uniformly in the t variable. That's what we have here, right? We have that mu tx minus mu ty is smaller than a constant times x minus y. This is the Lipschitz continuity in x, and the constant does not depend on t. Same thing for sigma here, right? So both mu and sigma have to be Lipschitz continuous. Now, we often require in ordinary differential equation something like mu and sigma being bounded. We don't quite need that. You can relax such a condition, and the way we relax it here is we assume that mu and sigma, okay, if they're bounded, that's great, but if they grow, that's okay, as long as they do not grow faster than linear function x goes to x. So we want mu tx squared to not grow faster than x squared, and same thing for sigma tx squared. So these are our assumptions: Lipschitz regularity of both processes and at most linear growth of both processes, of both functions, mu and sigma, and we want that to happen uniformly in the time t variable. Okay, if you assume these two properties of mu and sigma, 6.2 and 6.3, then there exists a solution. And by a solution, I just mean a continuous adapted process. There is a continuous adapted process that satisfies this stochastic differential equation, which again, you have to interpret in an integrated way. So this process is such that x of t minus x naught is equal to the integral of mu sxs ds plus the integral of sigma sxs dbs. First integral in the Lebesgue sense, second integral in the Ito sense, right? And you can do that for any initial data, and initial data at t equals 0 is still going to be a random variable, so potentially, so any initial data in L2 of omega, right? So you give yourself any L2 of omega, initial data x naught, and you can find a solution to the integral equation xt equal x naught plus integral of mu sxs ds plus integral of sigma sxs dbs. Now, do we know anything more besides the fact that the process is continuous? Yes, you can also show that this solution that you construct gives you a L2 random variable at every time t, and the L2 norm of xt are uniformly bounded with respect to t. So the supremum of a t of the expectation of xt squared is finite. Right, so this is a solution we can get, and you can ask yourself, is that solution unique? And yes, it is unique. It is unique in the class of continuous adapted processes that satisfy this solution. So they are in L infinity in time and L2 over the probability space. And the way you formalize this concept of uniqueness is in the following way. You say that if I have another continuous adapted process that also satisfies this condition, so the supremum of a t of expectation of yt squared is finite, and of course starts at the same initial data, then basically this process xt has to be yt. And what do I mean by basically has to be? I mean that the probability that x of t is equal to yt is 1. So the two processes are almost surely equal at every point of time t. Right, so that's our existence and uniqueness theorem, and the proof is going to be divided into two steps. In this video, we're going to prove uniqueness. So, assuming that I have an xt and a yt that are continuous adapted processes and satisfy this condition, then they have to be equal for all t with probability 1. Of course, assuming they have the same initial condition. And once we've proven that, in the next video, we'll do existence, and we'll see that some of the techniques that we develop for uniqueness will be used in the proof of existence, but the proof of existence is a little harder. So let's see the proof, let's see the ideas of the proof in their simplest form through the uniqueness argument right now. Okay, so let's start the proof of uniqueness. So what I have are two solutions of my SDE. So I have an xt satisfying this equation and a yt satisfying that same equation. And these processes are continuous processes adapted to the Brownian filtration, adapted and continuous. And they are such that the equations hold, and x0 is equal to y0 is equal to a fixed initial data, little x0 in L2 of omega. And on top of that, I know that the supremum of a t of the expectation of xt square, as well as the supremum of a t of the expectation of yt square, is finite. Okay, now I want to show that xt is yt for all t with probability 1. So the way we're gonna go about this is first consider the expectation of xt minus yt squared and show that this is 0 for all t, let's say in a finite time interval. So I'm going to fix a t and then a little t in the finite time interval 0 capital T, and I'm going to consider this expectation of xt minus yt squared. It's better to actually look at the L2 norm of xt minus yt, because then I can use triangle inequality for the L2 norm. Now, because x0 is equal to y0, and xt and yt satisfy the equation, I have that this is equal to the expectation. Let's actually just write that straight away as an L2 norm. The L2 norm of the integral from 0 to t of mu s xs minus mu s ys ds plus the integral from 0 to t of sigma s xs minus sigma s ys dbs, right? L2 norm of that. Now I can use triangle inequality and control that by the L2 norm of the part with mu minus the L2 norm of the part with sigma. Sorry, not minus, plus the L2 norm of the part with sigma, which is sigma xs minus sigma ys dbs. Okay. Now, remember the conditions that we have, right? We have conditions about the growth of the Lipschitz regularity of both mu and sigma. So in particular, so we have that mu s xs minus mu s ys, that is certainly smaller than a constant. So if I, let's say if I just as is, actually it's smaller than some constant which is square root of k, square root of 2 and times 2 times xs plus ys, and I have that sigma s xs minus sigma s ys squared, that's smaller than 4k times xs squared plus ys squared. And actually here I should have had, no, that's correct. Okay, so what can I do with that? Well, I can say first of all that the process s goes to sigma s xs minus sigma s ys has to be in H2 of 0 capital T, because xs and ys are uniformly in L2. And in the same way, using Cauchy-Schwarz, I can say that s goes to mu s xs minus mu s ys, Well, it's uniformly in L2, and that certainly makes it L1 of 0t as a function of t. But it's also L1 of 0t, let's put it this way, as a function of t. In the Lebesgue sense, almost surely. So I should write it probably like this. This would be better. This is in L1 of 0t for almost every omega in capital omega. So, okay, this is first of all reassuring. That means that what I'm writing here and what I'm writing there makes sense as a Lebesgue integral here and as an Ito integral here. More importantly, this tells me that what I'm integrating here is not just an L2 log process, which I would get from having, let's say, a continuous sigma, and my sigma is even Lipschitz continuous. It's better than that. It's an H2 process, so I can apply Ito isometry to the second term. And to the first term, it's a standard Lebesgue integral, or even for almost every omega, it's a Riemann integral, so I can apply Cauchy-Schwarz to that. Now, what happens when I do this? So I look at expectation of xt minus yt squared, raise that to the 1/2, apply Cauchy-Schwarz to the first term, and I pick up a square root of capital T times the integral from 0 to t of the expectation of xs minus of mu xs minus mu s xs minus mu s ys squared ds, and all of that is raised to the power 1/2. That's my first term after an application of Cauchy-Schwarz. And then the second term after an application of Cauchy-Schwarz, after applying Ito isometry, is the expectation of the integral from 0 to t of sigma s xs minus sigma s ys squared ds. And all of that is raised to the power 1/2. Okay, so now we're going to estimate that. And the idea here is that we have the Lipschitz continuity condition that guarantees that all of that is controlled by square root of capital T times square root of k in the first instance times the integral from 0 to t of xs minus ys squared, take the expectation of that, and ds. And for the second term, I get plus square root of k times expectation, integral from 0 to t, xs minus ys squared ds to the 1/2. And now putting these two things together, this is all smaller than 1 plus square root of t times square root of k times the L2 norm of the integral 0 to t of xs. So let's write it more like this. Expectation of the integral of xs minus ys squared ds, all of that raised to the power 1/2. Okay, so that's interesting. That means that if I look at the function g of t equal the expectation of xt minus yt squared, what can I say about this function? Well, I can say that g of t is smaller than this number that I'm going to call c. It's just a number that certainly doesn't depend on xs or ys. I mean, only depends on k and capital T. So it's smaller than c times the integral from 0 to c squared, I suppose, times the integral from 0 to t of g of s ds. And that is true for all t in the interval 0 to capital T. And we're going to say that really the only way you can have that is by having g of t constantly equal to 0. So let's see that now. Okay, so when I look at this relation here, this inequality, I'm thinking if it were to be an equality, I could differentiate on both sides and I would get that g prime should be a multiple of g. And so I would expect an exponential as a solution. Now, you can use the same sort of idea and think of it as not a equality linking derivatives in the function, as in an ordinary differential equation, but an inequality version of that. And then think of the way the exponential is obtained from a power series. And that would suggest that maybe we can prove the following claim, that is that g of t is always smaller than c2n tn divided by n factorial times g infinity for all t and for all n in n. Right? This is suggested by the fact that, well, you look at this, and of course this is telling you, if you control g by its supremum, that g of t is smaller than c squared times t times g infinity. But then, you could iterate that reasoning. That's the idea. But let's forget where the idea might be coming from and just check that it does work. So we do that by induction to prove the claim. We can start at n equals 0 even, not just n equals 1. For n equals 0, it's obvious because g of t is certainly smaller than the supremum of g of s over all values of s. And that's what you get for n equals 0. Now we assume it's true for n equals 1. Sorry, we assume it's true up to some n. And then we need to prove it for n plus 1. But what have we got? We've got that g of t is less or equal than c squared times the integral of 0t g of s ds. But then the induction assumption tells us that g of s is smaller than c to n, s to the n, n factorial, g infinity, ds. And then I can compute this integral and I get c to n plus 1 divided by n factorial times an entire derivative of Sn, which is Tsn plus 1 divided by n plus 1, so times Tn plus 1 divided by n plus 1 multiplied by g infinity, which is exactly what I wanted. C to n plus 1, Tn plus 1, n plus 1 factorial, g infinity. And that proves the claim. Okay, so I know that my g of t has to satisfy this induction property. But now what happens if I send n to infinity? Well, if I send n to infinity, I get 0 on the right hand side. So therefore, g of t has to be smaller than the limit as n goes to infinity of c to n, so c squared times t to the n divided by n factorial times g infinity, and that limit is 0. And that is for all t. Okay, so my g of t has to be 0. That is to say that the expectation of xt minus yt squared has to be 0 for all t. And that implies that x of t equal y of t almost surely. Therefore, x of t equal y of t almost surely. Is that what the statement of the theorem tells us? Not quite, but very close. So what does that tell us? That these two things are equal almost surely for every t. It means that for every t in 0t, there exists a set, a t, in sigma, which has probability 0, and such that for every omega not in that set, xt of omega is yt of omega. Now I want to put all of these ATs together. As usual, I can't do that if I have uncountably many of them. But if I restrict my attention to the rational, then I can find a set A with probability 1, which will be the union of all the AT, with probability 0, such that for every t and for every omega not in A, xt of omega is yt of omega. Now, okay, that is to say that outside of A, xt of omega is yt of omega for all rational values of t, but in the meantime, xt and yt are continuous processes. That is to say, they are almost surely continuous. And that's what we've called a continuous process. So if I throw away the set where xt might be t goes to xt might be discontinuous and the set where t goes to yt might be discontinuous, then I get a new set B, which is probability 0. So that's the union of the set A we had here, the set of discontinuities of this, and the set of discontinuities of that. So this is the union of 3 sets of probability 0. And then for every t in 0t and for every omega not in B, xt of omega is equal to yt of omega. And that is exactly saying that the probability that xt equal yt for all t, 0 to t, well, it's the probability of the complement of B, and so it's 1. And that concludes the proof of uniqueness for the theorem. And notice this argument here, that was the key part of the proof. We realized that using the assumptions of the theorem, that the quantity we were interested in, the expectation of xt minus yt squared, had to satisfy a certain differential inequality or more integral inequality. And from that integral inequality, we derived the fact that g of t had to be 0, and that concludes our uniqueness argument. Now the existence argument is going to be similar. It's also going to revolve around understanding an appropriate integral inequality. We'll see that in the next video.